Hello friends, welcome to the session on digital electronics. In this session, we'll be discussing about one of the important digital circuit called as counter circuits. In this session, we'll be discussing about asynchronous counters. In this session, we will see what we mean by the concept of counter, what are the different types of counters, and we will go for the discussion of asynchronous counters. Friends, as you know that you are viewing this session on my YouTube channel, Learn with Prakash Kanade, and subscribe to the channel to see many videos on the subjects of electronics and computer science. So we will start the session with the question, what we mean by counters. Counters, you can say, is a sequential circuit or it is a logic circuit that is being used for the counting of the input square pulses. So in sequential circuit, we know that many times we need to apply square pulses to the circuit. And whenever we apply such clock pulses, then these clock pulses can be counted by a electronic circuit, and such circuit is being called as a counter. So since this is counting the input clock pulses, that is the reason the name of the circuit is counter. There are two types of counters. The first counter is being called as a synchronous counter, and another counter is being called as a synchronous counter. In case of a synchronous counter, the clock pulse is applied only to one flip-flop, and the output of the previous flip-flop will drive the clock of the next flip-flop. In case of synchronous counter, the clock pulse is being simultaneously applied to all the flip-flops. Asynchronous counter, they are also called as ripple counters, or many times they are called as the serial counters. And synchronous counters are called as the parallel counters. Because in case of a synchronous counter, the clock pulse is applied only to one flip-flop, and the output of which will drive the clock of the next flip-flop, and therefore they are serial counters or ripple counters. But in case of synchronous counters, the states of all the flip-flops are changed simultaneously, and therefore they are called as the parallel counters. So counter circuits can be built by making the use of the flip-flops. When you take number of flip-flops together and when they are connected together, then it is possible that you can construct the circuit of the counters. So as I told you, in case of a synchronous counter, the clock pulse is not simultaneously applied to all the flip-flops, but it is applied to only one flip-flop, and the output of the previous flip-flop will drive the clock of the next flip-flop. While in case of synchronous counters, the clock pulse is to be applied to all the flip-flops simultaneously, and therefore the state of the synchronous counter will change rapidly or at faster rate. And therefore, we can say that the synchronous counters are faster counters than that of asynchronous counters. But whenever we go for the design of the synchronous counters, then synchronous counters are difficult to design, and also they will require more hardware. That is, they will require more number of gates than that of asynchronous counters. Now we know that every counter will have a certain number of fixed flip-flop, and therefore every counter will have certain number of fixed states. And these number of states of the counter is being called as the modulo of the counter. And this modulo figure will indicate how many clock pulses this counter can count. Counters are very useful circuit because they are used in many digital circuits. Say for example, in digital watches, there is a clock generator which will generate the clock for every 1 second. And whenever such 60 clock pulses are counted, then it is equal to the 1 minute. And when 60-minute pulses are generated, then it is equal to 1 hour. So digital watches basically consist of the counters. Also, counters are used in calculators, in computers. So in computers, the whole operation is being controlled by the central processing unit. And every central processing unit will require a clock generator. So there we will be needed to make the use of counters. Also in analog to digital conversion or in digital to analog converters, we will be needed to make use of counter circuits. So counter circuits are very popular circuits and they are used in many devices. And as far as this session is concerned, we'll be discussing only about asynchronous counters. And maybe in another session, we will discuss about the synchronous counters. Now we will go for the simplest type of asynchronous counter, and this counter is being called as a 2-bit counter, or it is also called as the modulo 4 counter. Because this 2-bit counter can count 2 raised to 2, that is 4 clock pulses, and therefore this counter is being called as a modulo 4 counter. So a 2-bit counter can count 2 raised to 2, that is equal to 4 clock pulses, and therefore this counter is called as a modulo 4 counter. Now, whenever we want to construct the 2-bit counter, then we require the 2 flip-flops, and these 2 flip-flops are to be connected as shown in the diagram. So one can easily observe that the pulses which are to be counted are connected to the clock input of FF0, and the output Q0 is connected to the clock input of FF1. J and K terminal of both the flip-flops are connected together, and this is called as a T terminal, and it is connected to logic 1. So both the flip-flops are the toggle flip-flops, and whenever these flip-flops receive a complete clock pulse, then their output is toggled, that is the output is changed. Clear terminal are made common and preset terminal are kept open. So this is a counter which require 2 clock pulses, and this counter can have 4 steps. So initially, when we apply 0 to the clear input, all the flip-flops are clear, and therefore the initial output of the counter will be 0, 0. Now once it is 0, 0, then for normal working of the counter, you need to apply 1 to the clear input. When the first clock pulse is applied, then the output of FF0 will get toggled, and output Q0 will get changed to 1. And the output Q1 will not get changed, because the FF1 will not receive a complete clock pulse, since the output Q0 is changed from 0 to 1 only. So the output Q1 will get changed only when the Q0 changes from 1 to 0. When the second clock pulse is applied, then the output Q0 will get toggled again, and its output now becomes 0. And now the output Q1 will also get toggled, because now FF1 has received a complete clock pulse, and therefore its output Q1 becomes 1. And therefore, after the application of the second clock pulse, the output of the counter becomes 1, 0. When we apply the third clock pulse, then the output Q0 will get toggled. So every time when we apply the clock pulse, the output Q0 will get toggled, but output Q1 will get toggled only when the Q0 changes from 1 to 0. And therefore, after the application of the third clock pulse, the output Q0 becomes 1 and Q1 remains 1. When the fourth clock pulse is applied, then output Q0 becomes 0, and now Q1 also will get changed, and it will also become 0. And therefore, after application of the fourth clock pulse, both the outputs of the counters will become 0, 0. So one can easily observe that this counter has only 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. And therefore, we can say that this counter can count 4 clock pulses. So from the figure, one can easily observe that the input clock pulse is applied to the FF0, and output Q0 will drive the clock of the next flip-flop. So we have shown the truth table, and from the truth table, one can easily observe that after the fourth clock pulse, the initial output of the counter is being achieved, and therefore we can say that this counter can count only 4 clock pulses. Now we can draw the waveforms of the counter, and when we draw the waveforms of the counter, one can easily observe that initial output before application of the clock pulse is 0, 0. Therefore, output Q0 is 0 and Q1 is also 0. When we apply the first clock pulse, then at the trailing edge of the first clock pulse, the output Q0 will get changed to 1 and output Q1 will remain 0. After second clock pulse, the output Q0 again becomes 0 and output Q1 becomes 1. After third clock pulse, the output Q0 again becomes 1. So these waveforms are to be drawn as per the truth table of the counter circuit. And after the third clock pulse, output Q1 will continue to remain 1. But after fourth clock pulse, one can easily observe that both the outputs Q0 and Q1 will become 0. So from these waveforms, one can easily observe that when the 4 clock pulses are applied to the input at the output Q0, we will get 2 clock pulses. That is, the 4 clock pulses are divided by 2 and we will get only 2 pulses at Q0. And at Q1, we will get only 1 pulse, which is further divided by 2, so that we will get only 1 pulse at the output Q1. So every flip-flop will divide the input pulse by 2 in case of asynchronous counters. Now we can go for the construction of the 3-bit counter, and this 3-bit counter can count 8 clock pulses. 2 raised to 3 is equal to 8, and therefore this counter is being called as a modulo 8 counter. So 3-bit counter can count 2 raised to 3, which is equal to 8 clock pulses, and therefore this counter is being called as a modulo 8 counter. Now whenever we want to construct this counter, since it is a 3-bit counter, then we will require the 3 flip-flops which are to be connected as shown in this diagram. So the only thing is that we have added one more flip-flop, FF2, in the earlier diagram, and observe that the clock input of FF2 is connected to the Q1 output, and J and K terminal are connected together to T2, and all the T terminals are kept at logic 1. So all such counters, these are the up counters, means they are counting in upward direction. Now it is also possible that you can construct down counters also. And whenever you want to construct the down counter, then what you needed to do is that you need to connect or reset the initial output to 111 instead of 000. And also you need to connect the Q0 bar to the clock input or Q1 bar to the clock input of the next flip-flop instead of Q0 and Q1. So as far as the working of this counter is being concerned, then initially we can reset output of all the flip-flops to 000 by applying 0 to the clear input. And whenever we go on applying the clock pulses, then for normal work of the counter, the clear and preset must be kept at logic high. So when the first clock pulse is applied, output Q0 will get toggled and becomes 1. But output Q2 and Q1 will not get changed because these flip-flops have not received the clock pulse completely. And therefore, after first clock pulse, the output of the counter will be 001. Now when we apply the next clock pulse, the output Q0 will again get toggled and becomes 0. Now since the Q0 has changed from 1 to 0, now output Q1 will also get changed and it will become 1. But output Q2 will remain 0, and therefore after application of the second clock pulse, the output of the counter will be 010. So observe that output Q0 will toggle for every clock pulse. Output Q1 will get toggled only when Q0 changes from 1 to 0, and output Q2 will get toggled only when the Q1 changes from 1 to 0. So after third clock pulse, the output of the counter will be 011. And after fourth clock pulse, the output of the counter will be 100 because output Q0 changes from 1 to 0. Therefore, Q1 also will get changed from 1 to 0, and therefore Q2 will get changed from 0 to 1. So in this way, after the application of the fifth clock pulse, output of the counter will be 101. After sixth clock pulse, it will be 110. After seventh clock pulse, it will be 111. And when we apply the next clock pulse, then output of all the flip-flops will get changed to 0, and therefore the output of the counter will be 000. That is, we have reached the initial state again, and therefore we can say that this counter can have 8 states, and therefore this counter can count 8 clock pulses. So as shown in the diagram, we need to apply the clock pulse to only one flip-flop, and the output of the previous flip-flop will drive the clock of the next flip-flop. And we have shown the truth table, and from the truth table one can easily observe that after 8 clock pulse, the output of the counter is being reset to the initial state, and therefore this counter can count 8 clock pulses, and therefore this is a modulo 8 asynchronous counter. Now we can draw the waveforms of this counter, and from the waveforms one can easily observe that initially all the outputs are 0. Now these are the flip-flops. These are JK master-slave flip-flop that are used in these circuits, and therefore the output of the JK master-slave flip-flop will get changed only at the trailing edge and not at the leading edge. And therefore at the trailing edge, one can easily observe that after the application of the first clock pulse, output Q0 will get toggled and it will change to 1, while output Q1 and Q2 will remain 0. So after second clock pulse, output Q0 again changes, while Q1 also changes, but Q2 will not change. So in this way, we can draw the waveforms, and these waveforms are drawn exactly as per the truth table of the 3-bit counter circuit. Now, the advantage of drawing these waveforms is that we can check the output of the circuit at any instant of time. Say, for example, when I want to check the output of the counter after 4 clock pulse, then one can easily see that the output of the counter is 0, 1, 0, and 0. So after 4th clock pulse, the output of the counter can be checked from these waveforms. Also, one can easily observe from these waveforms that when the 8 clock pulses are applied at the input, at Q0 we will get 4 clock pulses. At Q1 we will get only 2 clock pulses. And at Q2 we will get only 1 clock pulse. So every time the input number of pulses are divided by 2. Similarly, we can go for the construction of the 4-bit counter. So as its name indicates, this is a 4-bit counter, and therefore this counter will require 4 clock pulses, and this counter can count 16 pulses, and therefore this counter is being called as a modulo 16 counter. So the only change that we will make in the earlier circuit, that we will add one more flip-flop in this circuit, FF3, and we will connect the clock input of FF3 to the Q2 output of the previous flip-flop. Now, whenever you draw the circuit diagram for the counter, you should note that it is also possible that you can call this flip-flop as FF0, FF1, FF2, and FF3. And you can apply the clock input to the FF0. So, many times in some books, you will find that the circuit diagrams are drawn like that. And also you will find that even though we will write Q0 over here, but Q0 is our least significant bit, and Q3 is our most significant bit. Also, one can easily observe that whenever you want to construct a down counter, then in that case, you need to connect the preset terminal together, and you need to apply 0 to the preset input so that the initial output of the counter will be set to 1, 1, 1, 1. And then you can count in downward direction. And whenever you want to count in downward direction, then instead of connecting Q0, you can connect Q0 bar to the clock input, Q1 bar to the clock input of F2, and Q2 bar to the clock input of FF3. So these changes you need to make whenever you want to construct a down counter. So it is possible that you can construct a up counter, and as well as you can construct the down counter. Now, when we construct the truth table, one can easily observe that initially we will apply the 0 to the clear input so that all the flip-flops are cleared and initial output of the counter will be 0, 0, 0, 0. And whenever we go on applying the pulses, then Q0 will get changed every time, but Q1 will change only when Q0 changes from 1 to 0. Q2 will change only when Q1 changes from 1 to 0, and Q3 will change only when the Q2 changes from 1 to 0. And therefore, one can easily observe that we are actually getting a binary number sequence whenever the pulses are applied to this circuit. So after application of the first clock pulse, we will get the output 0, 0, 0, 1, then 0, 0, 1, 0, then 0, 0, 1, 1, then 0, 1, 0, 0. And in this way, after application of the 15th clock pulse, we will get the output 1, 1, 1, 1. And when we apply the next clock pulse, then the output of all the flip-flops will become 0, and therefore we will get the output 0, 0, 0, 0. That is the initial output. So if I apply the 17th clock pulse, then again I will get the output 0001, and the same sequence is being repeated. And therefore we can say that this counter has 16 states, and therefore this counter can count 16 clock pulses. So this is the circuit explanation where we have shown that the clock pulse is to be applied to only one flip-flop, and the output of the previous flip-flop will drive the clock of the next flip-flop. Now the truth table will actually explain us the working of the counter, and from the working or from the truth table we can easily observe that this counter can count 16 clock pulses. Now we can draw the waveforms, and the waveforms are drawn as per the truth table of the counter. So initially all the outputs are 0, and when the pulse is applied, output Q0 will get toggled, and Q1, Q2, Q3 will remain same, equal to 0. When the second clock pulse is applied, output Q0 will get toggled to 0, and Q1 will get toggled to 1, but Q2 and Q3 will remain same. So in this way, after application of the 16th clock pulse, one can easily observe that all the outputs are equal to 0. And as I told you, initially when we apply 16 clock pulses, at Q0 we will get 8 clock pulses, at Q1 we will get 4 clock pulses, at Q2 we will get 2 clock pulses, and at Q3 we will get only 1 clock pulse. So friends, it is possible that you can construct the odd counter also. Say for example, if you want to construct a mod 10 counter, then for mod 10 counter you will also require the 4 flip-flops, because by using 3 flip-flops you can count only 8 clock pulses. And you need to make an arrangement in the circuit. An additional gate is required, NAND gate, and which is to be connected to the clear input in such a way that whenever the 10th clock pulse will appear, then the circuit has to reset to the initial state 0000. So it is also possible that you can construct such odd counters where the count is not in the powers of 2. So thank you friends for viewing the session. Hopefully you have understood what we mean by counters and how to construct the asynchronous counters. Thank you all for viewing the session.